Good morning. So I'm happy to chair this session about X-ray astrophysics. We have two talks now before the lunch break and before our group picture here. And the two speakers are Claudio Macculi from Rome and Noemi Bastidon from Northwestern University. Claudio is about to talk about the cryogenic anticoincidence detector for the ATHENA X-IFU.
Thanks, Andrea. And let me thank the organizer for having provided us the opportunity to show the status of the Cryogenic AntiCoincidence project inside the ATHENA X-IFU instrument. So I'm Claudio Macculi from National Institute of Astrophysics in Rome, and I'm going to talk about the status of this instrument, which is performed inside the large collaboration in Italy among INAF, Department of Physics in General University, CNRIFN, and Italian Space Agency. This is the outline of the talk. I will start with a few info about the non-X-ray background assessment at the X-IFU focal plane assembly that has an impact on the design of the X-IFU and obviously of the anti-coincidence detector. Requirement specification, electronics, the demonstration model, which is our last prototype developed and tested, requested as for other critical technologies from ESA to demonstrate, to enable the critical technologies. So I invite you to see this couple of posters, some programmatic aspects, and then the conclusion. So this is, if you would have some further information, you can have a look on this link for the ATHENA mission X-IFU. So this is just one slide to introduce ATHENA. I know that has been already introduced. The main point is that ATHENA has been conceived to answer in the context of the ESA cosmic vision to answer to these two questions about the hot and energetic universe. How does ordinary matter assemble into the large-scale structure we see today, and how do black holes work and shape the universe at all scales? So the proposal, the answer has been to propose this mission that will be launched by an Ariane 6 satellite having 7 tons weight, 7 kilowatts, and having on board two complementary instruments. One is a wide field imager, having a larger field of view with respect to the cryogenic instrument, 40 by 40 arc minutes with respect 5 million arc minutes for the cryogenic instrument. But the wide field imager has a good energy resolution, but not so narrow like the X-ray integral field unit, having 2.5 electron volts up to 7 kV. So, and the anti-coincidence detector, being a cryogenic instrumentation, is inside the X-IFU instrument. We have also silicon paroptics because ATHENA is a focusing observatory, having this effective area 1.4 square meter at 1 kV. So, good part of the science topic, of the X-IFU science topic, is related to high energy, high resolution energy spectroscopy of faint and diffuse sources like outscattered galaxies and so on. And to perform this task, it is necessary to reach this non-X-ray background level at the main detector array level, 510 to the minus 3 count centimeters squared second per kV in this energy bandwidth. Here, this is a known formula related to the detectable flux, that means the sensitivity of the instrument, which is proportional to the square root of the background induced particle over the main detector. So having fixed the area, the detector area of the main detector, we can only decrease the induced particle background. So the sources, the primaries for this source, for this particle are the so-called soft protons that are low energy particles that will be put away by having on board of the satellite a magnetic diverter. And then we have the other source, which is most interesting for us, is the galactic cosmic ray, protons, electrons, alphas, having energy from 100 MeV to GeV that cross the cryostat, depositing energy in the detector. So what we have performed is that by using JAM4, which is a Monte Carlo toolkit, widely diffused particle community, but it is, I mean, several years that is also diffused in the astronomy community. We have evaluated what is the residual particle background by starting from the mass model of the cryostat and the FPA, by having in input the particle, the galactic cosmic ray expected particle flux, and by adopting the so-called physics, the rules, the physics of interaction among the particles and matter. So here just to see that without any reduction techniques to suppress not only primaries but also the shower secondaries generating but that primaries, we expect a particle background which is a factor 40 more or less above with the requirements. So we have put, thanks to ESA, an effort to well evaluate this kind of particle background, and at present with this reduction technique we got expected flux at a level of the required level. So the design concept we have worked with this table about the requirement, the system constraint that obviously drive the design of the anti-coincidence detector, geometric ejection efficiency, detection efficiency, allocated power dissipation being a cryogenic instrumentation, time taking intrinsic that time. So by moving from the heritage inside the team, we have adopted as absorber of this detector semiconductor, which is like silicon. We will note that they develop a sub-Kelvin ballistic component with an event particle or photon deposit energy. It has been good for us because we have used this feature, so the thermal, as a flag to raise the veto, the particle veto. But since in this respect the detector works as a surface detector, we have, it has been necessary to cover the surface area by a network of the TS. So at present the concept is constituted by 4 trapezoidal absorber, silicon absorber pixel connected to a silicon rim by silicon beams realizing the thermal conductance. We have on board also deposited platinum ethers because it could be a point to be verified during the DM integration with at the chipset level with the TS array from Goddard inside the FPA produced by Hezron. What is the coupling effect between the two detectors? It is also interesting for diagnostic. And from here we move to this table, so the specification of our detector, having a full detector area of about 5 centimeters square from under micron thickness and up to 1 MeV of energy bandwidth. So this is the schematics of the services of the satellite of the X-IFU. About the electronics, this is the cold side having inside the detector the cold front-end electronics, and then we move to the dual assembly, out of the dual assembly with the warm backend, the warm electronics. These 3 boxes, green boxes, constitute the anti-coincidence electronics, and it is designed as follows. We have here the cold side, the cold part having the squid part we have 4 independent detectors, so 4 independent squid, 4 independent readout chain. This is important for the tolerant, failure-tolerant philosophy requested by the system, which is CNES, the prime of the X-IFU. No multiplexing, standard flux locker loop readout. This is the squid bias anti-ISIS performed by this Wolfram-10 electronics box for separated quadrant, and then we move to the Warnbeck electronics box that digitized the analog scene, the science signal from the Wolfram-10 and prepare the data packet to be moved to the instrument control unit. So we move now to close this part that at present I will just show to you what is the baseline that are 4 segmented. This is a segmented detector, but there is also an ongoing trade-off study to understand if a monolithic absorber could be better in terms of detector responsivity, ejection efficiency, dead time, and robustness. Obviously, there is also ongoing a study related to the TS layout, but this is at present our baseline to be deleted off with this one. Then another point has been the production process, which has been quite demanding because after we have produced the first dummy, we see that by handling this detector, it is a bit fragile. So we have understood a lot by producing several dummies. This is the list, and see the poster of Michele Biasotti about the fabrication process. This is the list of the process. The goal of this slide is that at present we are qualifying this list of processes to increase the detector production yield. The main result is the demonstration model of the anti-coincidence detector. This is the 1 centimeter square absorber, 525 micron thick, having on board 96 iridium gold TS in parallel connected. This is important for the ATHENA, as I said before. This is the bracket, copper gold plated bracket. This PCP squad has on board the thermometer and the squid. So this is one of the our important results, because we have seen one of the to be compliant with the detection efficiency requirement, it is required to have a low energy threshold that below 20 kV. What we have seen here detecting is a very nice low energy fraction, and also that the detector has also a good sun spectroscopic capability, because have a 20% of line broadening with respect to the 6 kV pulse. The other important point is that this DM is compliant with the related requirements, and here just to show you that we have injected in this, having on board the heaters, we have injected in the same times iron 55 photons to zero energy threshold, and also thermal pulses by the heater. And you see here data stream. This is a saturation, a plot of the saturation by the heater. This is quite important for us to evaluate the dead time of the detector. This is the thermal conductance plot, the transition curve, and to conclude this slide, after that we have verified standalone the detector with respect to its requirement. We have moved all the detector and the electronics to Esron. Thanks to Esron, for this picture, this is so now available to the Esron colleague to go ahead with the integration with the Goddard array. So some near-term activities. There is several tasks to be performed in the next couple of years. And first, we have to close the trade-off study to understand this option between monolithic and segmented. The other point is that we are also inside another contract in the context of a core technology program of ESA. In this respect, we are going by the end of this year to define the design of the what will be the proto-engineering model of the anti-coincidence detector, and we are going, thanks to an external contract, we are going to produce to analyze by FEM analysis two different geometries, monolithic and segmented. Then next year we have planned to reach, we have planned to reach the TRL5 as requested, and we are going to develop a second structural model having representative interface with the FPA. We are also developing, start now, a contract for the warm electronics breadboard. This is important because in this warm electronic, we will plug this warm electronic breadboard with the Proto-EM, just so we will have in 1 year a fully one readout chain from the detector, from the chip to the output of the squid. And then another important point is the end-to-end simulator. This is important for us to well understand, to produce, the goal is to use this simulator, the output of this simulator, to well assess the trigger logic of the detector. This is the conclusion we have already discussed. I have already shown you the main point. I want to highlight a couple of dates: the mission adoption review of ATHENA end of 2021, and the ATHENA launch in 2031 at present planned. Thanks.
Thank you. Nice talk. If we have questions for the speaker, there's one there.
Hi, so you mentioned that the devices were very fragile, and in the pictures that you're showing, you have the legs are silicon, correct?
We have a belayer. Yeah.
But the mechanical legs that connect the main detector to the substrate, those are just silicon beams?
Sorry, yeah, silicon beam. The absorber is connected to the rib by 4 silicon beams.
Why are you making them straight?
Why we make them
straight? Because you have, ones in one direction, ones in another
just
direction.
A simple solution. We have, it is important the thermal conductance, and from the structural point of view, it's clear.
Right.
But
I would have thought that putting a little bit of curvature would have, given it a little bit of spring.
Because you see the right angle.
So that it won't break as much.
You see the right angle, right? Okay. For the DM has not to be vibrated, but in the context of I've shown here that we have to produce by the end of this year the first structural model, the masks, foreseeing that the angle is not at 90 degrees, but it's a little bit shaped.
Okay, thanks.
This is important because in our previous analysis we have seen that there are hot points from the structural point of view, sure, but so we have, okay.
We have one last question, I think.
I don't understand why. Did you put that much TSs?
Sorry, why?
Why did you put that much TSs? Why only just few TS on the wafer instead of 100? It is not needed.
Why we have a lot of TS instead of few TS?
Yes.
Because what we have seen is that maybe there is part of the answer in the poster from Michele. We have performed in Genova, Professor Corrado Boragna has performed an analysis, and we have seen that it is important for us the low energy threshold and the rejection efficiency of the detector. And we have seen that given the thickness of the absorber, which is 500 micron, it is quite important the pitch of the TS and the number of the TS over the full area. So we have at present seen that it is necessary to have each TS at maximum 1 millimeter far each other. And we have also seen this response in our all the prototypes, and the evaluation performed in Genova matched very well the response we have seen in our previous prototypes.
Okay, then
Okay.
take the speaker again.